Okay, so this video is going to cover some of the calculus addendums to magnetic field effects. So the main three classes, of course, magnetic fields on point charges, magnetic fields on current segments, and then the big finale, which was the torques on current loops. And so, first of all, I've put down the rules that they were presented in the previous videos, QVB sine theta, ILB sine theta, and then the right-hand rules and stuff. And for these, we'll pretty much leave them exactly alone, but for those of you that may be in a position to understand, and this might help you, I did want to briefly mention the cross product. So vector cross product is a topic that's normally covered in Calc 3, I think, and that's certainly not a prerequisite for this class, so your knowledge of that is not required. However, many of you happen to have already been in Calc 3 or even have finished Calc 3, and this might be something that might help you. If you were looking at this whole expression and thinking two vectors walk in, velocity and magnetic field, and a third vector walks out, force, and that vector is perpendicular to the plane of the other two, you probably were thinking this is a screaming cross product, and in fact all this nonsense that we treat kind of separately can be encapsulated into a single cross product. So V vector cross B vector times Q will give you the force vector, and Q here, of course, doesn't have an absolute value sign. That will actually even flip the force for you. So if it's a negative charge, then the force will be in opposite direction than a positive charge. Again, if you've never heard of a vector cross product in your life, you will at some point. But if you have, then this may be informative for you as to how to tackle finding the force on a charged particle when it has a velocity v and a magnetic field b. Moving on, same thing here with the force here on a current segment. So ILB sine theta of the angle between I and B. This can also be represented as a cross product. We do not want to make I a vector though. We want to preserve it as just a number, but the L vector, the length of it, will make a vector with the assumption that the direction comes from the flow of current. So if we have say a length L of wire and the current flows this way in it, then the L vector is defined as the length with that direction in mind. So that allows us to turn that as well into a cross product. L cross B times I gives you the force. Again, that's the essence of a vector cross product. Two vectors walk in, a third vector walks out, which is perpendicular to the plane of the other two. And again, if you've never heard of a vector cross product in your life, ignore these and just use what was in those previous videos. That's what I'm going to use on the all of my discussions. It's what's in all the solutions, and that's because knowledge of vector cross products is not required. So, moving on to the final thing, really the main thing that there are some holes in the previous videos that I want to talk about is torques on a current loop. So this is right here, just to summarize what was in there. So if you have a current loop, something like this, it has a current I in it. It has an area A. This is a rectangle, so you get the area just by multiplying length times width. It sits in a magnetic field of some direction, and there's this construct called the normal vector, and the normal vector is basically a vector that points outward, perpendicular to the plane of the area, and the way that you get its direction is you wrap your fingers around the direction of the current, and your thumb gives the direction of the normal vector, like so. And that's useful because you can think of those always sticking together, and if someone just gives you the normal vector with a single arrow, they've told you everything you need to know about how that current is flowing in 3D space and which plane it is circulating in. And what we learned was that the magnetic field is going to give this current loop a torque, and the normal vector the torque is such that the normal vector wants to align with B. So let's say that the magnetic field is pointing like that, then if I put this current loop in like this, it's going to torque like this, whoosh, like that. That's the direction of the torque it's going to want to take. Okay. Oh, and I guess I should mention, if you have a number of turns, and then you just multiply by that. That, by the way, is commonly the case. That's why I included it here. If you have not just a single current segment, but you have a whole bundle of these, so you have a whole bundle of current segments, you can multiply this by n as well. So that is not exclusive to the torque formula by any means. It's just very often when we have torques on current loops, to magnify the effect, we do wrap a bunch of turns here, so we make a kind of whole coil there, just so that we get more torque. Okay, so I guess I can draw a visual representation of that last thing I was mentioning. Here's the magnetic field, and the normal vector points like this. Then this wants to align like that. Okay, so the normal vector wants to align with the field. That will be the direction of the torque. So I think in the videos, this torque was called counterclockwise or plus, but that's not really a sophisticated way of talking about torque. Now this is something I'm hoping that people even know from Physics 1, but just in case you don't, let me go ahead and talk a little bit Physics 1 review. Phys 1 review. This is of kind of the advanced method of notating rotation direction. Okay, so first let me give you a sense of why this needs to exist. Okay, so let's say I have something rotating like this. You could certainly call that counterclockwise. I put some dots on there so you could see it. And if, of course, it was rotating the other way, we'd call that clockwise. But that assumes that you can look at the rotation kind of flat ways down in the plane of the page. That's not always the case. So what if you were looking at the rotation on edge like this? Well, you can't really use the counterclockwise, clockwise notation. Okay? So how would you describe that rotation mathematically? And moreover, you'd have a little bit of a problem, because for a person looking over here, I can't rotate the camera, so let me tilt this a little bit. For a person looking from this side, they would say that that rotation is counterclockwise, and a person looking over here, looking at that exact same rotation, they would say that that rotation is actually clockwise. So we have an issue when you have an object that's kind of rotating, and we're looking at it from the edge view. A person looking over here would say, again, that is counterclockwise. And a person over here, that's the physics eyeball. If you haven't seen it, it's meant to indicate perspective. So that same rotation, a person over there would say clockwise. Now, they are, of course, both right. They're looking at the exact same object. However, they're of course looking at it from different sides, so that's why they're saying different things. And for us, looking from the edge view, we don't know whether to say clockwise or counterclockwise, because we're just kind of looking at it from the edge. We don't have that flat ways appearance. So all of that can be solved with this right-hand rule that is from Physics 1. And again, some people, this is old hat, and some people have never heard of this, so let's talk about it. All you do here is you, very similar to how we find the normal vector, you wrap your fingers around the rotation direction like so, and that is considered the direction of the rotation, so this way. Now what the heck is pointing this way? Absolutely nothing, okay? The rotation is here, but we say the rotation direction is like that. So if we were to draw this in here, okay, a person over here would do the right-hand rule and claim that the rotation direction was this way. Let's say they said that the angular velocity, let's say we were describing, which you may remember is omega. Okay, so they would say that if this person were looking, they would describe counterclockwise as pointing this way, so like that. And let's take a look over here. What this person would see, well, they would wrap their right hand also around there, and they would say it points away from them, which, hey, look, that agrees. So now we have that everybody is in agreement about what the angular velocity is, regardless of perspective. So if I wrap my fingers around it from over here, I get that. If I wrap my fingers around it from over here, I get the same thing. And if I'm, of course, looking on the edge view, well, then I also agree. And so if we're all going to agree, say for instance that this was the plus x direction, we would all agree that the angular rotation was plus I hat. Okay? Now, how do we visualize something sticking out when all the rotation is in another plane? I like to think of it as just rotation axis enhanced. So if we think of it, this thing has a rotation axis, right, like this, and we're just basically saying instead of the rotation axis is just being kind of an axle or a line, we're basically giving it a direction. We're saying it points this way rather than this way based on the right-hand rule of wrapping our fingers. So you can use this same convention for any of the angular quantities. You can use it for omega, the angular velocity, angular acceleration, or torque. Okay, these are all, of course, things that are of interest to us. Again, if you don't remember what these are angular velocity, angular acceleration, alpha, and angular torque. Excuse me, torque, tau. So I think on the homework there's a warm-up question where it just basically asks you to go back and either review, if you've seen this before, how to notate this, and if you've never seen it before, to kind of get you up to speed. Now, of course, we do need this on occasion, but if we are looking at something in this plane, if something is rotating this way, then we of course could call it counterclockwise, and we've just been notating that as plus, but plus what? Well, usually we reserve, if we're using the x and y axes for the plane of the page, then the z-axis is going to point out of the page, and when we say this, what we really mean by plus is plus k hat. So when we're looking at it like that, counterclockwise is plus k hat. And if we're over here and something's rotating this direction, if we call it clockwise or minus, what do we really mean? Well, wrapping our fingers around, that points into the page, which is opposite our z-axis, so that's actually just minus k hat. I think, realizing now, I messed it up on the previous page. So yeah, over here this was counterclockwise clockwise or negative, and if we're picking the z-axis to be out, then the torque would want to point into the page, so that would be minus k hat actually. So again, this is just a more sophisticated way of notating any of these rotational quantities so that we don't have any ambiguity. And then the final thing I did want to tell you about this formula before I kind of move forward to some other stuff is that the quantities n, I, a, and the normal vector are all actually consolidated into a single quantity called the dipole vector. So this is called the dipole vector, or also known as the dipole moment. I don't use dipole moment too much, but you may notice that notation from your chemistry classes, but I use dipole vector. And of course, in this case, it's the magnetic dipole. We'll find out before the end of this lecture that there are other types of dipoles, but this is the magnetic dipole. And so, why do we want to consolidate all these things? This is basically pulling together all of the properties of the current loop together. So, what's the current in them? What is each of their area? How many of them are there, and how are they oriented in space? So this is all the properties of the current loop, okay? And it's putting them all into one package simply so that we can say that that's kind of encapsulates the loop as a whole. This means, by the way, that the units of the magnetic dipole vector, well, current is of course in amps, area is in square meters, and then the rest are unitless, right? This is just a unit vector that places its direction, and this is just a number of turns. So the units of magnetic dipole are amp square meters. And so that also tells us not all of these quantities here are always positive. So it tells us that the direction, of course, of the dipole vector is given solely by the normal vector. And what that means is, in this video, instead of just calling it the normal vector, I'm just going to go ahead and call it the magnetic dipole. So they share exactly the same directions. They're always agreeing. So rather than say the normal vector of a current loop wants to align with the field, I'll just say that the dipole wants to align with the field. Okay, so that's the direction of the torque. And so we can actually consolidate this. Instead of just calling it by the normal vector, we'll call it the magnetic dipole vector here, because they're the same direction. And then notice here, this part, this is the magnitude of that dipole vector. So we can, in this construct, we can greatly simplify this notation. And if you're looking at that and thinking, hey look, two vectors walk in, magnetic dipole, magnetic field. There's a third vector, which is related to the sine of the angle between the first two. And remember, this torque is perpendicular to both of those other two. Can you make this a cross product? Yes, you can. So again, if you're comfortable with this, this is the simplest way to notate these things. So there you have it. The kind of sophisticated, more sophisticated way we packaged this up by basically taking a bunch of the variables and ramming them into a single quantity. Of course, the only reason we didn't put B in there as well is, of course, B is not a property of the loop. It's what the current loop is being influenced by. So these are all the properties of the loop, and then it's being affected by a magnetic field B, and that effect is given by this equation. Okay, that's one abbreviation that we use a lot. And then I had to take a moment there to mention the more sophisticated way that we talk about rotational quantities in calc-based physics, which again hopefully is familiar with you. If not, then hopefully that was a little helpful primer. Again, if the cross product means nothing to you, just ignore that. All the solutions will be using this stuff over here. And I guess the one thing I should do before I move on is show you where this formula even comes from. In the previous video, I totally just glossed over it. And so